Oh, so we keep going. There's one very important integral, just like it was the last time, and this is actually really popular pretty much for the semester as well, is if I have the integral of 1 to infinity, and this could be anything really, just any arbitrary number to infinity, of 1 over p to the x, and notice we have two examples of that, where that one is there, and this one down here. So if we have this happening, it converges automatically if p is greater than 1. So 2 up, and diverges if p is actually less or equal to 1. Hence the reason why this actually diverges. Okay. So it's a very important interval. It's called the p integral test, and we'll talk about that later, but its proper name, but that's what it's called, is p integral test, to see if it converges or diverges based off that fact. Okay. Now the last type of the second part of the integral improper integral test is a little interesting, and it's something you got to be very, very careful of. It's a little trick question when it comes to it. And these type of integrals as well, what if it's not continuous on one part of a to b? Okay, so it says given the integral of this, where we have bounds, where f is continuous except at b, so it's everywhere except the endpoint, or somewhere along in the middle. Therefore, we convert it as, the integral from a to t, where t is greater than a, so any number between a and b, where t gets arbitrarily close to b on the left side. So I know this is kind of weird what it means by that, but so let's say here's a and here's b, and t is somewhere in the middle. So this is going towards this one. What it means by a negative means it's going towards the left side of b. So numbers closer and closer and closer on the left side of b. Okay. And the opposite is going to be for number 2, where if it's not continuous on a but okay on b, therefore we're checking it to the right hand side of b. So again, here's my a, b, so it's not continuous here. So therefore, if t goes this way, it's coming from the right hand side towards that. That's what that plus means there. Okay. So same situation as the part 1 is if the integral exists, we can find it, therefore it converges. And if we can't, it diverges there. Okay. And then the last part is in between, which is the most interesting one of all, and again, the trickiest of all, because what if there's a value between a and b that doesn't work, but the boundaries do work? Therefore, we have to break it up, just like we did for the indefinite integrals with infinities, where we have the integral from a to b is broken up into the value we can't use themselves. So then, in other words, we have to do parts 1 and 2 again to do that kind of stuff. And that's pretty much what that means. Okay. So let's try some examples so you can see how those work out for each individual case itself. Okay. And I give you guys one right off the bat using a part 3 here itself. So you value each of the possible. So let's first look at the boundaries. If I plug in 3, we're good, right? Doesn't give me 0 at the bottom, which is good. If I plug in 8, that's also gives me good. So there's not 0 negative at the bottom. However, if you notice, there's a number between 3 and 8 that doesn't work for this. And that is when x equals 5. Because if x equals 5, we get 0 at the bottom, which is a big no-no, right, when it comes to it. So that's what this situation comes into play. So we're actually going to break up the integral into 2 parts and do them individually itself. Okay. So what this is saying is we're going to break this up into the integral from 3 to 5 plus the integral from 5 to 8. Just like that. And now it goes to step 1 and step 2 of the second part. So we're going to break up each one using its limit now. So we're going to have the limit as t goes to 5 to the left-hand side of this, plus tt, the limit as t goes to the right of 5 this time, of that. Okay, so if we take the integral, this shouldn't be too bad if you guys are wondering how to do this. I always put it into its form. This is negative 1/2, right? So add 1 gives you half. Or essentially this is a u substitution. Right, so d1. So the integral of u to the Gaussian just gives you here. Right, same process there. We'll evaluate it. This one was 3 to t. Oh, yeah, sorry, this is supposed to be a t here. These are supposed to be t. Okay, so plug it in t, see what we get out, right, and vice versa. So this is 2 on top of x, sorry, t minus 5 minus, you plug in 3 minus 5 plus same thing over here. You just take the limit as t goes to each one individually. So for this one, as t goes to 5 to the left-hand side, and this one going 5 to the right-hand side. Notice both of those go to 0. So we just plug it in. So this goes to 0 essentially, minus, this is going to be 3 minus 2 is negative 2, and mean positive 1. Oh, so the 1/2, I forgot about that. That's why it goes to 0. So plug it in 2. 3 minus 2. Yep. This goes to 0. This goes to 0. Plug this in. This is 1 to the 1/2 power. Oh, what am I doing? No wonder this is all wrong. There. Confusing myself. Shouldn't we do these so late? Let me start over right here. This is what I want to do. So let me just cross this off. Let's do it the proper way with the integrals. Try to be lazy here. Okay. That's what we get. Okay. Now, if t goes to 5, essentially just plug it in, right? So if I let 5 minus 5 gives you 0, so all that goes away. So we're just left with this. And notice this doesn't exist, which is a big no-no, right? So all that's gone. So essentially, all we care about is this part. Okay. So plug in 2. This gives you 3. So this is 2 radical 3. And again, plug in 5, that goes away, so we're just left with that there, right? Because it's technically imaginary, which doesn't count. So this converges. And there's your answer. Okay. So don't worry, that's one of the most difficult of them. Just have a fun at the beginning. Okay. Okay. All right, so this one, you got the same one, but let's use the first bound itself. Okay. So the exact same process, but now we're going to only use half the work, which is a good thing. So let's take the limit as t goes to 2 from the positive side, or from the right-hand side of this. Right, so you kind of see a template of each one individually, how it's going to be. Okay, so take the integral. So we already did it on top, so it's just going to be this value here. So plug in each one. So plug in 8. So 8 minus 2 is 4, or so minus 6, so it's going to be 2 radical 6, and then plug in t. And again, as t gets closer to 2 from the right, plug in 2, that just goes away. So you're just left with t.